Hi everyone, I am presenting PPT on Unit 6 oscillator, that is LC oscillator. So we had seen the applications and types of the oscillators in previous PPT. So this LC oscillator in the radio frequency oscillators and RC oscillator, that is in the audio frequency oscillators. In radio frequency oscillator, there are many different design of the sine wave oscillator used in the radio and communication equipment, usually using the some form of resonant circuit to generate the signal at radio frequency from several tens of kilohertz to 1 gigahertz and maybe above. This model describes some popular types of LC sine wave oscillator. Frequency control in RF oscillators. The different types of frequency control networks we are used in high frequency sine wave oscillators. That networks are LC networks, quartz crystal network, and ceramic resonators. In LC networks, we will study the Hartley oscillator and Colpitz's oscillator. And crystal oscillator is the combination of RLC, resistance, capacitance, and inductance. First we will see the tune oscillator circuit. The variety of circuit can be built using, it is shown in figure, providing the tuning in both the inputs. So this is the generalized diagram, amplifier X1, X2 and X3. So we will see the parameter in detail, X1, X2 and X3. So analysis of the circuit reveals that the following types of oscillators are obtained when the reactance element are as designated. So in this table, resonant reactance element, that is X1, X2 and X3 in this diagram, and using that there is the types of the oscillators. In Colpitts oscillators, X1, X2 and X3. So X1 and X2 we use the capacitors and X3 we use the inductance. While in Hartley oscillators, that is the vice versa, X1 and X2 are inductance and X3 is capacitance. Then tune input and tune output. In X1, X2 we use the LC, the series of the inductance and capacitance. Now in basic LC oscillators tank circuit, we use the inductance and capacitance and one switch that is connected to the B and A, and the field is producing in the inductance, that is called as the electromagnetic field. We applied the battery. The circuit consists of an inductive coil L and capacitors. The capacitors store energy in the form of electrostatic field that we know, that produce the potential across the plates, while the inductive coil store its energy in the form of electromagnetic field. So that is shown in figure. The capacitor is charged up to the DC supply voltage, whatever supply we applied. Then the switch is position A when the capacitor is fully charged, and switch changes its position to B. The charged capacitor is now connected to the parallel across the inductive coil. So the capacitor begins to discharge itself through the coil. Voltage across the capacitor start falling as the current through the coil begins rise. This rising current set up an electromagnetic field around the coil which resists the flow of current. When the capacitor C is completely discharged, the energy that was originally stored in the capacitor and C as an electrostatic field is now stored in the inductive coil, and L as an electromagnetic field around the coil's winding. This current charges up capacitor C with the opposite polarity to its original charge. Then the C continues to charge up until the current reduces to 0, and electromagnetic field of coil has collapsed completely. The energy originally introduced into the circuit through the switch has been returned to the capacitor, which again has an electrostatic voltage potential across it. It is now the opposite polarity. Then capacitors now started discharge again back through the coil, and whole process is repeated. So using in this figure, that is charging and capacitor discharging, the switch between the A and B. Then the potential LC circuit, the amplitude of the oscillatory voltage decreases at each half cycle of the oscillation and will eventually die away to 0. To understand this, we will see the damped oscillations in the damped oscillation circuit. Here small r lightly damped and longer time. Okay. So in this waveforms, it is finally at the longer time it is die out, and it is the shorter time die out. So if the resistance is small, then longer time, and if the resistance is large, then heavily damped, that is the shortest time. That is the oscillations we get. So in general we calculated the 37%. The frequency of the oscillatory voltage depends upon the value of the inductance and capacitance in LC tank circuit. We now know that the resonance to occur in the tank circuit, there must be frequency point where the value of the Xc, the capacitive reactance, is the same as the XL, that is the inductive reactance. The inductive reactance XL equals to capacitive reactance Xc. Therefore, they cancel out each other out, leaving only the DC resistance in the circuit to oppose the flow of current. Now, to understand better, we use the resonant frequency. This is the diagrammatically here we have to I am explaining resonant frequency F versus the reactance in ohm. So we use here reactance in ohm in inductance as well as the capacitance. So that is XL minus XC. So that is the XL, that is linearly showing, and XC, that is the Xc is showing, and the center of the point here is the reason is the capacitive react, that is Xc greater than XL, means reactance of the capacitance is greater than the reactance of the inductance, and this other half side, that is reactance of the inductance is greater than the reactance of the capacitance, and the center of the point, that is XL equals to Xc, means reactance of the inductance equals to reactant of the capacitance. That point is called as the resonant frequency f of t, ft. Now here where fr, that is the resonant frequency, is in hertz, that is the between, that is fr, not ft. L, that is the henries, and C is the farads, means inductance in henries and capacitance in farads. Then the frequency at which this will happen is given as XL as usual. Inductance, reactance of the inductance, that is 2 pi FL, and Xc, that is reactance of the capacitance, that is 1 by 2 pi Fc. As resonance, XL equals to Xc, that means 2 pi FL equals to 1 by 2 pi Fc. So here we calculate the resonant frequency, that 2 pi f square L by equals to 1 by 2 pi C, then f square equals to 1 by 2 pi square by LC. Finally, taking the under root, f equals to under root 1 by under root 2 pi square by into LC. So finally you will get, then the simplifying the above equation, we get the final equation, that is called as the resonant frequency of the LC oscillator. So that as well you know, fr equals to resonant frequency equals to 1 by 2 pi under root of LC. So using this you can calculate the Hartley and Colpitts oscillators. In Hartley oscillators there is the 2 inductance, 1 capacitance. Colpitts oscillator there is the 2 capacitance, 1 inductance. So that is the addition of the L and C. So that will be seen next PPT. Here where L is the inductance in henries, C is the capacitance in farads, and Fr is the output frequency in hertz. Now here we taken the basic transistor LC oscillator circuit. We use the single transistor, that is the common emitter amplifier, C circuit. In input side we use the inductance L2, and then collector side we use the inductance L with the C, and we are getting output that. So using this, here is the 180 degree phase shift between L2 and L, and that is the amplifier circuit for this transistor. So we are getting 180 degree phase shift or 180 degree phase shift at the amplifier. Here the bipolar transistor is used as a LC oscillator amplifier, with the tune LC tank circuit acts as a collector load that we see in the figure. The another coil L2 is connected between the base and the emitter of the transistor, whose electromagnetic field is mutually coupled with that coil L. Mutual inductance exists between the two circuits. The changing current flowing in one coil circuit induced by the electromagnetic inductance a potential voltage in the other, so as oscillation occurs in the tune circuit. Then this electromagnetic energy transferred from coil to coil L to L2. The voltage of same frequency as that in tune circuit is applied between the base and the emitter of the transistor. So in this way, the necessary automatic feedback voltage is applied to the amplified transistor. The LC oscillator is therefore a sinusoidal oscillator or harmonic oscillators, that more commonly called, and LC oscillators can generate the high frequency sine wave for use at radio frequency. Types of application with the transistor amplified being bipolar transistor. Then the harmonic oscillators come in many different forms, because there are many different ways to construct an LC filters network and amplifier with the most common. So using this we can, there is the types of the oscillators. First is the Hartley oscillator, Hartley LC oscillators, then Colpit LC oscillators, then Armstrong oscillators, and fourth is the Clap oscillator. So in your syllabus there is the Hartley, Colpit oscillator, sometimes the crystal oscillators also they may ask. So next PPT we will discuss in details the Hartley oscillator and Colpit oscillator. So thank you very much, students.